This video is going to talk about the strain energy release rate, building off of the derivation of the Griffith crack criterion and connecting to the idea of fracture toughness. So in the Griffith criterion, we established that there was an energy balance between the new surfaces that were created by a crack extending, and that's related to this variable gamma S, the surface energy, and the elastic energy that was released as the crack grew. And that was given by this term here on the right, where sigma is the stress, A is the crack length, and E is the elastic modulus. We rearranged this to get an expression for the critical stress, which looked like this, and where all of these variables have the same meaning as before. This is for the plane stress condition. If we are in the plane strain condition, then we add the term 1 minus nu squared in the denominator. The Griffith criterion gives us essentially the critical stress where the crack will begin to propagate depending on these material properties and the crack geometry itself. It didn't, however, consider what would happen if there was also plastic deformation occurring in the material. So let's look at that next. So if plastic deformation occurs as the crack is growing, there are a couple of things that happen. The first is that the crack tip can be blunted. This means that the crack tip is not quite as sharp because there's some plastic deformation occurring just ahead of the crack tip. The mechanism of fracture also then will depend on the plastic work that is done. We're going to use this symbol here, gamma sub p, to indicate the plastic work that's done as the crack advances. That variable, gamma sub p, depends on the crack speed, the temperature, and the material. Now, if we have a brittle material, then the Griffith criterion mostly holds because the plastic work done is small. And when I say small, we're talking about less than maybe 10% of the surface energy there. If the material is not brittle, though, and we do have plastic deformation occurring at the crack tip, then we need to take both the surface energy and the plastic work done into account in the energy balance of crack propagation. And we will do that by using gamma S plus gamma P, so the surface energy plus the plastic work done, instead of just the surface energy term as we do our energy balance. Let's see how that works out. So here we have the sort of modified Griffith criterion, which now takes into account this new energy term with the surface energy and the plastic work done. And this top equation here is for plane stress, and the bottom is for plane strain. If it's the case that the plastic work done is much greater than the surface energy term, such that this relationship here is true, then we can rearrange this equation to find the following. So you'll notice here that now we have the plastic work done in the equation instead of the surface energy, but still we have these sort of material properties over here, we have crack geometry down here, and we have this critical stress at which the crack will propagate. So it was proposed by Irwin that the crack will propagate when that stress reaches a critical value. And Irwin defined this as a crack extension force, which is called G. And the crack extension force is connected to, again, the energy of the material, which is released as the crack moves, and how that varies with crack length. So G is defined in the following way. So it's the change in the internal energy with the crack length. So as we saw before when we were looking at the Griffith criterion, that elastic energy in the material is defined as pi a squared sigma squared divided by E. And so in carrying out this derivative, essentially, we find that G is equal to pi A sigma squared divided by E. This is, of course, for plane stress, and so if we have plane strain, we have to remember about our 1 minus nu squared term. But let's dive in a little bit more and see what it is that G really represents. So G is often called the strain energy release rate. It is the energy per newly created surface as the crack grows. G is sometimes called, though, the crack extension force. And in that case, it's the force acting on the crack normalized by the length of the crack. And even though these units look different here between the two, they turn out to be the same once you write the joules in terms of newtons instead. So somewhat like the fracture toughness, the strain energy release rate both describes the current state of the crack in a particular material, depending on some material properties, but also has a critical value at which crack growth will take off. So it's just another measure of describing what is going on in the material while cracks are present. Let's take a look now at how we can relate G, the strain energy release rate, to the fracture toughness of a material. If we start with the equation that we derived for G before, we can rearrange to get the following. Then we take the square root of both sides, and we can notice that what we have over here on the right side is equal to K1. So that, again, the 1 is for mode 1 loading, and this is assuming that y, our geometry factor, is equal to 1. So we end up with the relationship like this. Or if we want to have G in terms of K, then we have this equation right here. So the strain energy release rate is equal to K1 squared divided by E, the elastic modulus. So whether we know K or we know G, the strain energy release rate, we can easily move back and forth between them for a given material, assuming that we also know the elastic modulus. Now, I haven't yet talked about plane stress or plane strain, and so really what we should do is that we should put a little prime on here so that we can use this as our most general equation, and then we can just define the value of E prime depending on if we have plane stress or plane strain. So here are the values for E prime depending on plane stress or plane strain. And that is the conclusion of this video related to the strain energy release rate.